Okay, so in this video, we're going to look at some examples of voltage division. I've actually got 2 pages of notes here, and it's going to be 4 examples because voltage division is very important, and I want you to see several applications. The first one is a textbook application. We've got just straight 2 resistors in series with the known voltage across them. We know that the 12-volt source is going to tend to drive current clockwise around this circuit. I can see that we're encountering the plus sign on each of these voltages first, so that means that the passive sign convention will be satisfied, where everything is happy. It's just a matter of applying the 2 equations. So let's go ahead and do V1 is going to be equal to Vs times R1 over R1 plus R2. That's going to be 12 volts times 10 ohms over 10 ohms plus 20 ohms. And if you plug that into your calculator, you get that V1 is equal to 4 volts. And then similarly, we can calculate V2. V2 is equal to Vs times R2 over R1 plus R2, which is equal to 12 volts times 20 ohms over 10 ohms plus 20 ohms. And if you put that in your calculator, you end up with it being 8 volts. The 2 things that I always want to check in a voltage division problem, do those 2 numbers add up to the total voltage? And yes, 8 plus 4 is equal to 12 volts, so I'm satisfied there. Does the larger resistor get more of the voltage? And yes, V2 is 20 ohms, that's the larger resistor, and V2 is the larger voltage. So both of those reality checks turn out to be correct, and so therefore I'm pretty confident that these results are correct. Okay, let's look at a little bit more complicated example. In this case, it's not such a textbook example. There are 4 resistors instead of 2, and those 2 resistors that we want to find the voltage across, those are not in series with one another. But we can simplify the circuit down to one in which voltage division is applicable. So the first thing I'm going to notice is that the 5 ohm resistor and the 1 ohm resistor are in series with one another. So our equivalent for those 2 is equal to 6 ohms. So I could redraw the circuit, or I'm going to cheat here because space is limited, and I'm just going to sort of show what the 6 ohm resistor would look like right there. So if that's 6 ohm, and I'll take this out so it's not quite in the way. So I've now replaced all of that with a 6 ohm resistor. Now you can see that the 6 ohm resistor is in parallel with the 3 ohm resistor. So the equivalent resistance for those 2 is going to be, because there are only 2 of them, I'm going to do product over sum. 6 times 3 over 6 plus 3, that's 18 over 9. That will be 2 ohms. Now it's definitely time to redraw the whole circuit. So let's go ahead and redraw it. And now we are down to just 2 resistors, and lo and behold, they are in series with one another. And so this is going to be 2 ohms. Now there might be one hesitation, and that is, hey, we combined the 3 with the 6, but the 3 was the one that had the voltage we wanted. So we wanted to know the voltage across the 3 ohm resistor. But if you notice, what we really wanted to know was, what is this voltage? I'll call that point A, as compared to this voltage, which I'll call point B. Well, that point A and point B are unchanged when the 3 and the 6 combine together. So when the 3 and the 6 are combined into an equivalent resistance, point A still remains right here, and point B still remains right here. Sometimes it helps to label additional nodes that weren't labeled in the original circuit diagram so that you can be sure that the voltage that you're finding is still the voltage that you were looking for. So now, in fact, we do have V2 being plus to minus. So now the circuit that I've drawn down here in red is ready for the application of voltage division. We're asked to find V1 and V2. Just one little thing to note here is that I've reversed the V1 and the V2 from the first example. So you just got to be careful as to which resistor is labeled V1 and which resistor is labeled V2. So V1, that's going to be Vs times R1 over R1 plus R2. That is going to be 10 volts times, now R1 is 10 ohms. And that will be divided by 10 ohms plus 2 ohms. And when we plug that into our calculator, we end up with 8.33 volts. And then V2, this is going to be Vs times R1 over R1 plus R2. This will be 10 volts times 2 ohms over 10 ohms plus 2 ohms. and therefore V2 is equal to 1.67 volts. Do those two add up to the total voltage of 10 volts? Yes, they do. And does the larger resistor get the more voltage, get more of the voltage? And yes, it does. So I'm feeling good about those two numbers. So this is a good example of a place where it wasn't apparent at first that voltage division would have been appropriate, but it ultimately was. Okay. Third example. Now I've included that ground node. You remember we talked about the ground node at the start of the lesson today. And what I'm asking for is V sub x. And notice that V sub x doesn't have a plus and minus. I'm only talking about the voltage at a particular point. What that really means is that V sub x is relative to ground. So V sub x, I want to know what is the voltage at that point relative to ground. And so if I were to redraw that, where does that actually appear? Well, the voltage, the positive terminal is here, and the negative terminal is here. So if what I'm looking for is Vx, which is in between the 5 ohm and the 15 ohm resistor, it might have been confusing at first whether I was asking for the voltage across the 5 or I was asking for the voltage across the 15, but I'm actually asking for the voltage across the 5. So this is actually really easy. Once you've identified which voltage you want, you say V sub x is equal to 10 volts multiplied by the resistance that you want, and we want 5 ohms, divided by the sum of the two resistances, 5 ohms plus 15 ohms, and V sub x then, that's going to be 1/4 times 10 is going to be 2.5 volts. And that is all there is to that example. The only tricky part there was figuring out that V sub x is a voltage at a point, which means that it is relative to ground, and therefore it has to be across the bottom of those two resistors. And we come to our fourth example. Now this one is the same geometry as the second example, but now I'm asking for this voltage right here. Remember, before I was asking for this voltage and this voltage, but no longer am I asking for those two voltages. I'm asking for V5. Okay, so let's follow the same path that we followed last time. We know that the 5 ohm and the 10 ohm are going to be in series, so our equivalent is going to be 15 ohms. I will go ahead and expand this out. So I'm going to have the 15 volt here. I'm going to have a 15 ohm resistor here. I'll have a 15 ohm resistor here. 15 ohms and 15 volts. And then I've got another 15 ohm resistor here. Now, one thing to notice, I can no longer label anything in this new circuit as being V5. V5 is a portion of this 15 ohm resistor right here. But I can't get just a portion of that resistor, so I can't label V5. V5 doesn't exist on this diagram. And that's a little troubling, but we're going to find how to find V5 regardless. So we've got 15 in parallel with 15. We know that if those two resistors have the same value, then their equivalence will be half of the original resistance. And then that 7.5 ohm resistor, let me go ahead and show that. Let me go ahead and show that circuit. That's going to be, I've got 15, that's going to be 15 volts. And now I've got 15 ohms and 7.5 ohms. Okay, now what I could find is I could find the voltage across either of those two resistors. I could even go ahead and toss in a reference node here. And so we can either list that as the ground node or the reference node. And what that means is that if I find this voltage right here, I'll label that as V sub A. Well, that will actually be relative to ground. But that V sub A is the same V sub A that's right here. And as a matter of fact, that's the same V sub A that's right here. Which means that if I find V sub A in the third circuit diagram, I can go back up and know that V sub A in the first circuit diagram. We're actually kind of flashing ahead to the next lesson, but I thought that this would be a good thing for us to see right now. So let's say V sub A is going to be equal to 15 times 7.5 divided by 7.5 plus 15, and that works out to be 5 volts. So now we know that this is 5 volts. And we also know that this one is 5 volts. And most importantly, we know that this one is 5 volts. Because guess what? Now we have two resistors in series, the 5 ohm resistor and the 10 ohm resistor, and we know the total voltage that appears across both of them. Because that total voltage is 5 volts. I know that 5 volts is right here. Part of it is going to appear across the 5 ohm resistor, and part of it is going to appear across the 10 ohm resistor. This is my reference node, so this will be 0 volts down here. And so we have a perfect classic voltage division circumstance. So I can say V5 is equal to VA times 5 ohms divided by 5 ohms plus 10 ohms. VA is 5 volts, so I'll go ahead and write that in here. And then I can find that V5 is equal to 1.667 volts. So just to remind you what we did, we combined the 5 ohm and the 10 ohm in series. We got this second circuit diagram right here. Once we knew that circuit diagram, we combined the 15 and the 15 in parallel. We got the third circuit diagram right here. We were able to use voltage division to find V sub A from that circuit diagram. And then we were able to move up and see that V sub A appeared all the way back up to the first circuit diagram, which gave us the opportunity to apply voltage division across this path right here to the reference node. And that allowed us to calculate what was the total voltage, or the voltage across the resistor V5.